Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. In this episode, we will travel to Barnard Star, the second closest star system to the Sun and the closest of all stars in the northern celestial hemisphere. Barnard Star is a red dwarf, invisible to the naked eye, with a mass of about 15% of that of the Sun. Its distance from the Sun is just 5.96 light-years. Discovered in 1916, Barnard Star is noteworthy not just for its proximity to our Sun but for its astronomical peculiarities. The star is renowned for its exceptionally high proper motion. Proper motion refers to the apparent motion of a star across the celestial sphere when viewed from Earth. This motion is mainly due to the star's actual movement through space, combined with our solar system's motion. Barnard Star has the second highest known proper motion of any star, second only to Greenwich 1830. It moves across the night sky at a rate of 10.3 arcseconds per year, meaning over the span of a human lifetime, its movement would be traceable to the naked eye when measured against more distant stellar backgrounds. Its movement would, over a human lifetime, amount to about half of the angular diameter of the Moon. The rapid motion of Barnard Star across the celestial sphere hinted at its closeness to Earth. The reason being, generally, stars that are closer to us seem to move more quickly across the sky due to the effect of parallax. The significance of its discovery was the realization that our immediate stellar neighborhood was still full of surprises and that there were possibly many more celestial bodies yet to be discovered. Barnard Star is named after the American astronomer Edward Emerson Barnard, who is renowned for his astrophotographic work and keen observational acumen. He's especially known for his work in astrophotography, having captured numerous images of the Milky Way, comets, and other celestial phenomena. His keen eye for detail allowed him to make several significant discoveries during his career. Recognizing the star's rapid movement against the more distant stellar background, Barnard was credited with its discovery in terms of its significant proper motion, and the star subsequently became popularly known as Barnard Star. While the name Barnard Star might imply possession or discovery in the conventional sense, it's important to understand that many stars and celestial objects are named in honor of the astronomers who made significant observations or discoveries related to those objects, not necessarily the first to ever document them. In the case of Barnard Star, its name commemorates Barnard's observation of its significant proper motion rather than its initial discovery. The star was catalogued and observed before Barnard's 1916 identification of its high proper motion. However, its unique motion-related characteristics were highlighted and brought to prominence by Barnard. The apparent magnitude of Barnard Star is 9.5. But what does that mean? The magnitude system is a bit counterintuitive. The lower the number, the brighter the object appears. Conversely, higher magnitude values represent fainter objects. The brightest star in the night sky, Sirius, has an apparent magnitude of about -1.46. The faintest stars visible to the naked eye in a dark, clear sky typically have magnitudes around +6 or +6.5, depending on individual eyesight and sky conditions. Given that Barnard Star has an apparent magnitude of 9.5, it's much fainter than the faintest stars most people can see without optical aids. As a result, you cannot see Barnard Star with the naked eye, even on a clear, dark night. To observe Barnard Star, you'd need a telescope or a good pair of binoculars. In the night sky, Barnard Star is located in the constellation Ophiuchus. As mentioned, it's invisible to the naked eye, but you can still imagine it's there. Ophiuchus is best viewed during the northern hemisphere's summer months, from about June to August. This is when the constellation is highest in the night sky. In those summer months, Ophiuchus is visible for much of the night. Look for it in the southeastern sky after sunset and watch as it moves across the southern sky and sets in the southwest before dawn. More specifically, Ophiuchus can be seen from locations between the latitudes of +80 degrees and -10 degrees, meaning all of the populated parts of the northern hemisphere all the way down to just south of the equator. When you're looking at the constellation Ophiuchus, you're looking towards a region of the sky that's located between the center and the edge of the Milky Way, in the direction of our galaxy's central bulge. Ophiuchus is situated to the northwest of Sagittarius, where the actual center of the Milky Way is located. So, when you're looking at Ophiuchus, you're essentially gazing into one of the richer and denser areas of the Milky Way's starry disk, but not directly at its core. Within and around Ophiuchus, you'll see numerous stars, star clusters, and patches of nebulosity that are part of the Milky Way's disk. The region is packed with interstellar material, and with minimal light pollution, you can appreciate the dense band of our galaxy stretching across this region. But of course, all of this is tens of thousands of light years from the Sun and Barnard Star. Now let's imagine traveling to Barnard Star and looking at the Sun from there. At a distance of approximately 5.96 light years, the Sun, viewed from Barnard Star, would appear much brighter than most stars in the sky, but it wouldn't be the brightest object. In terms of apparent magnitude, it would shine at about magnitude +0.5, making it one of the brightest stars in the night sky, comparable to some of the brighter stars we see from Earth like Vega. However, it would not outshine the very brightest stars we're familiar with, such as Sirius. The area behind the Sun would be the opposite of what we see when viewing Barnard Star, meaning you would see the outer, less packed region of the Milky Way behind the Sun. The Sun's location in the sky from Barnard Star would be in the direction of Orion. However, the closest star to Barnard Star is not the Sun, but Ross 248, another red dwarf. Ross 248 is located 5.41 light-years from Barnard Star, and would be too faint to be visible to the naked eye. What do we know about the speed of Barnard Star compared to the Sun? To get the star's true motion relative to the Sun, we need to combine its tangential velocity, that is, from its proper motion and distance, with its radial velocity, that is, movement toward or away from us. Barnard Star is moving toward the Sun at about -110.6 kilometers per second. The negative value indicates motion towards us. Derived from its proper motion and its distance from us, its tangential motion is approximately 90 kilometers per second. To calculate the total relative velocity, v, we can use the Pythagorean theorem. Thus, we can calculate that the total velocity of Barnard Star relative to the Sun is approximately 142.7 kilometers per second. It is currently approaching the Sun and will continue to do so for thousands of years. Based on its trajectory and velocity, astronomers estimate that Barnard Star will make its closest approach to the Sun in about 9,800 years from the present. At its closest approach, it will be about 3.75 light-years away from the Sun. After reaching this point of closest approach, Barnard Star will then begin to move away from the solar system. Alpha Centauri is also moving towards the Sun and will be even closer at the time of the closest approach of Barnard Star, so Barnard Star will never be the closest star to the Sun. The age of Barnard Star has been a topic of interest for astronomers. Determining the exact age of stars can be a complex task, often involving a combination of observational data, stellar modeling, and comparison with stars in similar evolutionary states. Red dwarfs evolve very slowly. Given its spectral characteristics and its relatively low activity level, apart from occasional flares, it's believed that Barnard Star is quite old, even by astronomical standards. Estimates for the age of Barnard Star have varied. Some studies have suggested it could be as old as 10 to 12 billion years, making it nearly as ancient as the universe itself, which is roughly 13.8 billion years old. Other estimates propose a somewhat younger age, but still, it's generally agreed upon that Barnard Star is an elderly star, much older than the Sun, which is 4.5 billion years old. Barnard Star might even be among the oldest stars in the Milky Way galaxy. Understanding the age of Barnard Star is crucial not just for the sake of the star itself, but for what it can tell us about the evolution and life cycles of red dwarfs. Since red dwarfs make up the majority of the stars in our galaxy, gaining insights into their characteristics and lifetimes is essential for our broader understanding of the Milky Way's stellar population. The rotation of a star, or its rotational period, also plays a significant role in understanding various properties and behaviors of that star, including its magnetic activity and age. For stars like our Sun, the rotation can influence the solar activity cycle, which has implications for space weather and, in broader terms, the conditions of habitability for nearby planets. Observations indicate that Barnard Star has a rotational period of approximately 130 days. This is much longer than our Sun's average rotation period, which is about 25 days at its equator and longer at higher latitudes. The rotation period of a star is often linked to its magnetic activity. Stars with rapid rotation tend to have higher levels of magnetic activity, which can result in more frequent and powerful flares. Given Barnard Star's relatively long rotation period, one might expect it to exhibit lower levels of magnetic activity, though exceptions do exist. This aligns with much of what is observed. Barnard Star is relatively quiescent for a red dwarf, though it does exhibit occasional flares. A star's rotation can also provide hints about its age. Generally, stars spin down over time due to the loss of angular momentum, especially through stellar winds. The fact that Barnard Star has a relatively long rotation period suggests that it's an older star, which aligns with other estimates of its age. Red dwarfs are often more active in terms of stellar activity, such as flares and star spots. Barnard Star, being a red dwarf, is known to exhibit variability and can produce flares. In 1998, a significant flare event from Barnard Star was observed by astronomers using the Hubble Space Telescope. Over just a few minutes, the star's brightness increased by a factor of 50. This event was notable because of its intensity and the fact that such powerful flares were not commonly associated with quiet, older red dwarfs like Barnard Star. The observations indicated a temperature spike to 8,000 Kelvin, notably higher than its standard readings. Such intense flares were unexpected for older stars like Barnard Star. Although flares remain a mystery in many respects, they are often attributed to powerful magnetic fields. These fields can inhibit the movement of plasma, leading to sudden, energetic outbursts. Typically, young and fast-spinning stars possess these strong fields, while older ones like Barnard Star rotate at a slower pace, making such dramatic flares an unusual occurrence. Studies have also indicated that the star generally has a calm nature, with minimal evidence of variation in brightness and potentially just one observed star spot over a 130-day span. These unique flare events have led researchers to view Barnard Star as a potential key to understanding other similar stars. By investigating its X-ray and UV emissions, scientists hope to gain insights into the older M dwarf stars that populate our galaxy. This research could have profound implications for the study of life beyond Earth. Planets in the habitable zones of M-dwarf stars would be in close proximity, making them highly susceptible to solar flares, strong stellar winds, and plasma ejections. By 2019, additional ultraviolet flares were recorded, along with an X-ray flare. The cumulative effects of these flares indicate a potential significant atmospheric loss for any planet close to Barnard Star over extended time frames. This information further underscores the star's significance in understanding the environments around older M-dwarf stars and their potential to host life. Given the randomness of flares, allocating time with the largest telescopes for studying any random event even in the closest stars is ineffective. Instead, the proximity of Barnard Star and the randomness of its flares makes it an excellent choice of study for amateur astronomers. If many people are observing or recording it at any time, chances are we will have lots of good data should new flares happen. In any case, the 1998 flare event changed the perception of how older red dwarfs can behave. Previously, it was believed that as these stars aged, their activity levels decreased significantly. However, the flare from Barnard Star indicated that even old red dwarfs can still produce significant outbursts of energy. In the grand scheme, this event served as a reminder of the dynamic and ever-changing nature of stars. Even as they age, stars like Barnard Star can still produce surprises that challenge our understanding of stellar evolution and behavior. Barnard Star is of specific interest when it comes to the study of radial velocity and its causes. Radial velocity is a fundamental concept in astronomy, and its applications span a wide range of astronomical phenomena, from studying binary star systems to detecting exoplanets. Radial velocity is the speed at which an object is moving directly towards or away from an observer. It's the along the line of sight component of the object's velocity. In astronomy, this is typically measured using the Doppler effect. When an object, like a star, moves towards or away from us, the light it emits is blue-shifted towards the blue end of the spectrum or red-shifted towards the red end, respectively. By measuring this shift in the light's wavelength or frequency, astronomers can determine the radial velocity of the object. One of the primary uses of radial velocity in modern astronomy is the detection of exoplanets. As a planet orbits a star, it exerts a gravitational pull on the star, causing the star to move in a smaller, counter-orbit. This motion causes variations in the star's radial velocity, which can be detected from Earth as Doppler shifts in the star spectrum. By measuring these shifts, astronomers can determine not only the presence of a planet but also derive its mass and orbital period. However, genuine planetary signals must be distinguished from those introduced by stellar activity. Star spots, flares, and other phenomena can create noise in the data or even mimic planetary signals. The field of radial velocity has seen considerable advancements in the last few decades. Modern spectrographs can measure radial velocities with precisions of a meter per second or even better. In systems with multiple planets, the combined gravitational effects produce complex radial velocity patterns. Advanced data analysis methods are used to tease apart these signals and identify individual planets. Radial velocity is often used in tandem with other methods, like the transit method, where planets are detected by the tiny drops in brightness they cause when they pass in front of their stars, to confirm detections and gain more information about the planets. Outside of exoplanet research, radial velocity measurements are crucial for understanding the dynamics of galaxies, studying the expansion of the universe, and more. While the radial velocity method is often used to detect planets, stellar activity can also induce radial velocity variations, and these false signals have been a subject of extensive study in the exoplanet community. Stellar activity like star spots, analogous to sunspots, and stellar flares can introduce radial velocity variations that might mimic the signatures of orbiting planets. Differentiating between genuine planetary signals and those caused by stellar activity is crucial. As for Barnard Star, it has long been monitored with regard to radial velocity variations because of its proximity to Earth, and its relative quiescence compared to other red dwarfs makes it an appealing target. In 2003, there was research that addressed possible radial velocity variations in Barnard Star believed to be attributed to magnetic activity rather than the presence of a planet. By studying these variations, astronomers aim to get a better understanding of the star's magnetic cycle and activity patterns. Recognizing and understanding such non-planetary radial velocity signals is essential to accurately detect and confirm exoplanets. Barnard Star is a prime example of the low-mass, low-temperature stars that dominate our galaxy in numbers. The mass of a star plays a pivotal role in dictating its life cycle, luminosity, and ultimate fate. For Barnard Star, its mass is estimated to be around 0.144 to 0.160 solar masses. This places Barnard Star firmly in the category of M-dwarf stars, which are stars with less than half the Sun's mass. Such stars have incredibly long lifetimes, burning their nuclear fuel at a leisurely pace, and can shine for tens of billions of years, far outlasting stars like our Sun. The temperature of a star determines its color. The surface temperature of Barnard Star is estimated to be around 3,100 Kelvin, equivalent to 2,827 degrees Celsius or 5,121 degrees Fahrenheit. This relatively cool temperature for a star gives it its characteristic red hue. In comparison, our Sun, which appears yellow-white, has a surface temperature of about 5,778 Kelvin. The cool temperature and low mass of Barnard Star also mean that its energy output, or luminosity, is much lower than that of the Sun. If you were to replace our Sun with Barnard Star in our sky, Earth would receive only a tiny fraction of the light and heat it currently does, making our planet a frigid world unsuitable for life as we know it. What about the metallicity of Barnard Star? Metallicity, in the context of astronomy, refers to the proportion of a star's content that is made up of elements other than hydrogen and helium. It's a crucial parameter that can shed light on the star's origin, age, evolutionary history, and even its potential to host planets. Metallicity can hint at which population group a star belongs to. There are three broad stellar populations: Population 1, metal-rich, younger stars found in spiral arms and disks of galaxies; Population 2, metal-poor, older stars found in the halo and nuclear bulge; and Population 3, hypothetical very metal-poor or metal-free stars from the early universe. Given its metallicity, Barnard Star would likely be classified as an intermediate star, between Population 1 and Population 2. Barnard Star has a metallicity that's lower than that of the Sun. This supports that Barnard Star is older than the Sun since the early universe had fewer metals. Over time, succeeding generations of stars have produced and distributed more metals into the interstellar medium, which then gets incorporated into new stars. Metallicity can influence the formation of planets around a star. Generally, higher metallicity stars are more likely to have gas giant planets, given that there are more heavy elements available to form planetesimals and planetary cores. However, it's still debated how metallicity affects the formation of smaller, terrestrial planets. The confirmed and refuted detections of planets around Barnard Star make it a valuable data point in understanding these relationships. although the general understanding is that Barnard Star possesses a subsolar metallicity. Some new studies could revise this understanding. The field of astrophysics is dynamic, with new data and improved observational techniques leading to refined or even altered conclusions about known astronomical objects. If Barnard Star has a metallicity comparable to that of the Sun, several implications and discussions arise. A higher metallicity could suggest that Barnard Star formed in a region of the Milky Way that was enriched with heavier elements. This might, in turn, hint at a somewhat younger age for the star than previously thought, or it might suggest that older regions of the galaxy were more metal-rich than assumed. As mentioned earlier, higher metallicity has been linked to an increased likelihood of forming planets, especially gas giants. This could either reinforce or bring new discussions to the table about the potential presence of planets around Barnard Star. If Barnard Star and potentially other stars of its age are found to have higher metallicity values, this could also have implications for our understanding of the metal enrichment process of the Milky Way. As previously discussed, metallicity is a parameter in classifying stars into various population groups. An increased metallicity could lead to a re-evaluation of Barnard Star's classification. The history of the search for planets around Barnard Star is rich and illustrative of the challenges and evolution of exoplanetary science. In the early 1960s, Dutch-American astronomer Peter van de Camp, working at the Sproul Observatory at Swarthmore College, announced that he had detected a wobble in the motion of Barnard Star. He interpreted this wobble as evidence for the gravitational influence of one or more unseen companions, likely planets. Van de Camp's method of choice for detecting planets was astrometry. Astrometry involves measuring the precise positions of stars in the sky. When a star has a planet or planets orbiting it, the gravitational pull of the planet can cause the star to wobble slightly in a small circle or ellipse, which is referred to as the star's astrometric wobble. If this wobble can be detected and measured, it's possible to infer the presence of a planet, as well as estimate the planet's mass and orbit. Van de Camp used data from the Sproul Observatory to track the position of Barnard Star over many years, looking for such a wobble. Van de Camp had been observing Barnard Star from 1938, attempting, with colleagues at the Sproul Observatory at Swarthmore College, to find minuscule variations of 1 micrometer in its position on photographic plates consistent with orbital perturbations that would indicate a planetary companion. This involved as many as 10 people averaging their results in looking at plates, to avoid systemic individual errors. By the early 1970s, Van de Camp had refined his observations and claimed the existence of 2 Jupiter-sized planets orbiting Barnard Star. One was believed to have an orbit of 12 years, and the other 26 years. His claims generated considerable excitement because they would have been the first exoplanets ever detected. However, Van de Camp's claims became controversial. Other astronomers had difficulty replicating his findings, leading to skepticism about the purported planets. Further investigation revealed that the changes made to the Sproul Observatory's telescope, specifically modifications to its optics, might have introduced systematic errors into Van de Camp's data, causing the observed wobble. The claimed wobble was smaller than the precision typically achievable with ground-based astrometry at the time, making it especially susceptible to various sources of error. Stars can have intrinsic variability or movements that aren't related to planets. Some argued that the observed motions of Barnard Star could be attributed to factors other than planets. Over time, and with the accumulation of more precise data and improved techniques, the consensus shifted against Van de Camp's claim of planets around Barnard Star. By the late 1970s and 1980s, with the advent of more precise observational instruments and techniques, no credible evidence for these planets could be found. The general consensus among astronomers was that the planets Van de Camp detected did not exist. Fast forward to 2018, technology and methods for detecting exoplanets had advanced considerably. A team of astronomers using high-precision radial velocity instruments announced the discovery of a super-Earth planet around Barnard Star. This planet, named Barnard Star B, is believed to have at least 3.2 times the mass of Earth and orbits its star every 233 days. Unlike the earlier claims, this discovery was backed by data from multiple observatories and is widely accepted by the scientific community. Barnard Star B stands out as a captivating discovery, if it exists, not just because of its location around one of the nearest stars to the Sun, but also because of what it might tell us about exoplanets in general and the conditions around red dwarf stars. Here are some key details about the planet. Barnard Star B is classified as a super-Earth. This designation means it's more massive than Earth but significantly less so than gas giants like Uranus or Neptune. Its relatively close proximity to its parent star might suggest it could be warm enough to support liquid water on its surface. However, given that Barnard Star is a dim, cool, red dwarf, the planet actually sits just outside the star's habitable zone and is likely a frozen world, with average temperatures estimated to be around -170 degrees Celsius, equivalent to -274 degrees Fahrenheit. Its distance from Barnard Star is about 0.4 astronomical units, AU. To put this in context, Mercury, the closest planet to our Sun, is about 0.39 astronomical units from the Sun. Given its cold estimated temperatures, it's unlikely that Barnard Star B is hospitable to life as we know it. The planet's atmosphere, if it has one, and its potential for any subsurface oceans or other interesting geophysical features, remain topics of interest and speculation. Barnard Star B is a prime target for future observations, especially with advanced telescopes like the James Webb Space Telescope. These observations will help determine its atmospheric composition, surface conditions, and other characteristics. Given its proximity to Earth, it's one of the most accessible exoplanets for detailed study. In essence, while Barnard Star B might not be an Earth twin, it is a valuable discovery in the exoplanetary field. Studying this super-Earth will deepen our understanding of planetary formation, the conditions around red dwarf stars, and the diversity of planetary bodies in our galactic neighborhood. It should be noted, some reservations have been made about the discovery. After its initial announcement in 2018, the planet's presence was generally accepted based on the amassed radial velocity data. However, as is typical in science, especially with groundbreaking findings, subsequent analyses and observations sometimes bring initial conclusions into question. In July 2021, a study emerged that cast doubt on the existence of Barnard Star B. Researchers reanalyzed the data using different methods and came to the conclusion that the signals previously attributed to a planet could instead be the result of stellar activity or other sources of noise in the data. Red dwarf stars like Barnard Star are known for their variability and can exhibit complex magnetic phenomena and star spots. These can create signals in the radial velocity data that mimic those of an orbiting planet. The challenge for astronomers is to distinguish the genuine planetary signals from those caused by the star's activity or instrumentation noise. The 2021 study presented a compelling argument, but it's essential to remember that in the realm of exoplanetary science, such debates are not uncommon. As techniques evolve and more data becomes available, our understanding gets refined. Sometimes this leads to the confirmation of previously detected planets, while other times it might lead to their retraction. As of today, the debate is still ongoing, with some astronomers in favor of the planet's existence and others skeptical. Further observations, especially with newer and more precise instruments, will likely help clarify the situation. It underscores the dynamic nature of science and how our understanding is always evolving as we get more data and refine our methodologies. One way to refine our knowledge on possible exoplanets around Barnard Star is what is called Monte Carlo analysis. Monte Carlo analysis, also known as Monte Carlo methods or simulations, refers to a broad class of computational algorithms that use repeated random sampling to obtain numerical results. The name Monte Carlo was inspired by the famous casino in Monaco and reflects the technique's reliance on random processes. Here's an overview. Monte Carlo methods in their core principle rely on the law of large numbers. By simulating a process or system many thousands or even millions of times, you can approximate the expected outcome for that process or system. For any system or model you want to analyze, there are certain inputs that can vary. In a Monte Carlo simulation, you define possible values for these inputs and the probability distribution that describes the likelihood of each value. For each iteration of the simulation, random values are selected for each of the inputs based on their defined probabilities. With the randomly selected inputs, the model's outcome is computed. Selecting random values and then computing the outcome is repeated many times, often thousands or millions, to generate a distribution of outcomes. Once there is a large enough distribution of outcomes from many iterations, you can analyze them to understand the probability of different results, the expected value, the variance, and other statistics. This is used in many areas, like finance and engineering. Monte Carlo methods are often utilized in astrophysics and exoplanet studies to handle uncertainties, analyze data, and interpret possible outcomes from observations. Given the inherent complexities and numerous variables involved in detecting exoplanets, these methods are particularly useful for extracting meaningful information from the data and understanding the level of confidence we can place in potential detections. In the context of Barnard Star, or any other star, for that matter, Monte Carlo simulations can be applied in several ways. Radial velocity measurements, which look for wobbles in a star's motion due to orbiting planets, come with noise and uncertainties. Monte Carlo simulations can be used to generate a large number of potential radial velocity curves based on the noise level and uncertainties in the data. By comparing these simulated curves with the observed data, researchers can determine the likelihood of a planet being the cause of any observed wobbles. If planets transit in front of their host star, they can sometimes cause small changes in the timing of these transits. Monte Carlo simulations can help determine if these variations are due to additional planets or just noise. After a potential planet detection, it's essential to estimate the probability that this detection is a false positive, i.e., not a planet. Monte Carlo methods can simulate many scenarios, such as background binary stars, to estimate how often these can mimic planet signals. If there's evidence of multiple planets around a star, their gravitational interactions can affect their orbits. Monte Carlo simulations can explore a wide range of initial conditions and see which configurations are stable over long timescales. Regarding Barnard Star specifically, given its high-profile nature and the history of claimed planet detections, any new claims of planets are scrutinized thoroughly. Monte Carlo analyses are part of this rigorous assessment, helping to determine the reliability of the data and ruling out other possible explanations for observed signals. Indeed, in a 2013 research paper, Monte Carlo analysis was used to refine planet mass boundaries for Barnard Star. Using radial velocity measurements from the Lick and Keck observatories, taken over a period of 25 years, and applying Monte Carlo analysis for both circular and eccentric orbits, upper masses for planets out to 1,000-day orbits were determined. Planets above 2 Earth masses in orbits of less than 10 days were excluded, and planets of more than 10 Earth masses out to a 2-year orbit were also confidently ruled out. It was also discovered that the habitable zone of the star seemed to be devoid of roughly Earth mass planets or larger, save for face-on orbits. Now, to be sure, Would you be able to travel to Barnard Star? Barnard Star, due to its proximity to our solar system, has naturally attracted attention from those interested in interstellar exploration. While we have not sent any spacecraft to Barnard Star and there are no current missions planned to go there, the star has been discussed in the context of hypothetical future missions. Here are a few projects to note. Breakthrough Starshot. This is an ambitious initiative announced in 2016 that aims to develop a proof-of-concept fleet of light-driven nanocrafts that would make the journey to the nearest star system, Alpha Centauri, in just over 20 years. Although the primary target is Alpha Centauri, the technology, once developed, could potentially be adapted for other nearby stars, including Barnard Star. Daedalus and Icarus. Long before Breakthrough Starshot, there were the British Interplanetary Society's Daedalus, in the 1970s, and Icarus, started in 2009, studies. These were theoretical designs for uncrewed interstellar probes. While the primary target for Daedalus was not Barnard Star, it was among the candidates considered for an interstellar mission due to its proximity. Interstellar travel presents enormous challenges. Even though Barnard Star is very close in astronomical terms, it's still almost 6 light-years away. The vast distances involved require novel propulsion methods, like those proposed in Breakthrough Starshot, to get there in a reasonable time frame. Current propulsion methods would take tens of thousands of years to reach such distances. While Barnard Star offers a tantalizing target for exploration, any mission to the star remains in the realm of future possibilities and theoretical designs for now. However, with rapid advancements in space technology, the coming centuries might see humanity venturing beyond our solar system. If you are still awake and want more content, go ahead and check out our other episodes, and if you want to help creating even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now, thank you for joining this trip, and have a beautiful and wonderful night, with sweet dreams, once you get there.